This is a football game, and this is an AI watching it. It knows which team is which, it knows where the ball is, and right now it's tracking possession. I built the whole system using only Python. No premium API, no paid trackers, just simple Python. And most importantly, it's free to run. So you can run it on your local machine, whether you have Apple Silicon or Windows-based machine. So stick around and I'll show you how you can build such an advanced system and how every piece of it works. In part one, I trained a custom YOLO model to detect football, the players, the referee on a football pitch. If you haven't seen it, links in the description. By the end of the video, we ended up with the YOLO model doing its own default things, drawing its own bounding boxes and saving files. It works perfectly well, but it's useless if you want to do anything with it. So in this video, we're taking complete control of it. So in this video, we're going way deeper and taking things to the absolute next level. We've got a few massive upgrades to build into this project. First, hardware optimization. We're taking absolute control of YOLO's output. I don't care if you're running Apple Silicon, Nvidia GPU, or even a standard CPU. So our main goal here is to ensure it runs as smoothly and as swiftly as possible. Right, secondly, we have custom annotations. We'll replace the standard, more like a cluttered bounding boxes with a bit more clean, professional visuals. So we're gonna do floating triangles for the players, a bit more dedicated ball marker for the ball, and we're gonna add a ring for the referee. Right after that, we're building the brain behind it. We want the system to auto-detect things we never even trained it on, like running zero-label team assignments to figure out who's who on the pitch and calculating live ball possession with a dynamic shifting bar. And finally, we're turning pixels into physics. We're calculating true player speed in real time. So the first thing is hardware optimization. So out of the box, the biggest problem with the YOLO model is that it doesn't know nothing about your hardware, and it's completely reliant on genetic defaults. That means it might blindly choke your CPU to death while perfectly a good powerful graphic card sits completely idle right next to it. And the problem is that because it doesn't know where to look at. So we have to change the strategy of how the model runs. So we need to make the script understands your machine and actively tell the model exactly what hardware it has at its disposal. Right, so let's talk about Apple products specifically. If you have an M1, M2, or even M5 like myself, a YOLO can leverage your GPU using MPS, which stands for Metal Performance Shaders. But there's a massive catch. So the problem is YOLO relies on operation called NMS, non-maximum suppression, to clean up overlapping boxes. But right now, MPS does not natively support that operation. So if you run the code completely stuck on a Mac, it will throw a fatal error and a crash mid-pipeline. And so to fix this, we need to inject a fallback command before PyTorch even initialize. Okay, now let's get into coding. So first off, let's delete the old code and start fresh. We want this to be lean and fast. So we kick things off with a quick fallback environment variable for Mac users. So PyTorch does not crash on unsupported operation. Then we bring our standard libraries, the argparse, the YOLO, CV2, and Torch. Next, we set up the argparse. This is just let us quickly swap our model weights, the video source, and also the settings right from the command line without having to edit the script every single time. Now the smart hardware detection. So this is the most crucial line for guaranteeing maximum speed on any machine. And so instead of guessing, this actively checks your system and automatically assigns the fastest hardware available. So whether that is your Mac GPU, the MPS, or just an Nvidia card, which is going to refer as 0 here, or fall back to the CPU. Next, we're prepping the output. Before firing up the model, we just create our output directory and grab the video properties to set our frame per second or the FPS and initialize the OpenCV video write. Next, we need to create the for loop, and here's where the heavy lifting happens. So we need to feed the model our auto-detected device and flip two major performance switches. So the first one is the stream. So we turn it to true, basically to process the video frame by frame so you don't max out your RAM and crash your machine. And secondly, half to true. So this basically precision weight. So currently it's 32 and we switch it to 16-bit math. We actually can switch it to 8 bits weight. And this basically cuts the computational weight in half, giving you massive speed boost with zero loss in accuracy. Then we save and clean up. So inside the loop, we grab the plotted frames, show the live preview, and write them to our output file. And finally, we break the loop, we release the video write, and close the windows. So finally, .mp4 saves perfectly without any corruption. All right, and that's it. So let's run it. So first, as always, we need to activate the virtual environment by doing source ven/bin/activate. Once it's activated, then we can go ahead and run the script. Now, I wanted to do side-by-side comparison, and let's look at the actual results. So I've put them side by side so we can really see the difference. On the right is the default out-of-the-box YOLO setup, and on the left our newly optimized code. And remember, this is running on the exact same device. And look at the difference in real-time rendering. The default version is dropping frames and is struggling to keep up, but our dedicated version is running incredibly fast and buttery smooth. So that's exactly why we take the time to optimize our hardware. Now the model runs smoothly and fast. The second thing that we're gonna do is smart annotations. Now the problem with the original YOLO model, it comes with these bonding boxes and all the classes shares the same boxes and it gets crowded, really difficult to see, and they're just meaningless. So we're gonna ditch them all and replace them with a bit more custom drawing. It's gonna be like triangles for the players and a ring for the referee, also triangle for the ball, and you can turn them on and off as well. So let's get started. Okay, so bonding boxes are good for debugging, but they're not good for custom annotations and just for any visuals. So we're ditching all the bonding boxes and replacing them with more custom annotations, custom markers. And this is what we're gonna do and how we're gonna do it. So the issue with the standard boxes, they're not the best because they overlap, they clutter the screen. So that's the reason that we're gonna change them with more custom drawing. So instead, we're gonna replace them with the floating markers triangles, hover right over the player's head. And by doing so, they're gonna be completely out of the way. And so visually, it's gonna look better. Now, how do we draw a floating triangle? So the math is composed of 3 different steps. So first we find the horizontal center of the box. Then second, we target the top edge and offset it upwards. That gives us the triangle's tip. And finally, we'll push outwards and upwards from the tip to set our top left and top right corners and connect those 3 points, fill it up with color, and then that's it. We created our custom marker. Then it's just a matter of rendering it. So we pass those 3 points to OpenCV's fill poly function and it draws a solid triangle directly into the frame. Then we apply a similar trick to the ball, tagging it with a glowing yellow ring that follows it dynamically. And just like that, we created a custom professional markers. Part 3, we're gonna do team detection or team assignments. This is the most exciting part to build, at least for myself. So the goal is for the model to detect and understand the difference between team A and team B. Because at the moment, YOLO sees only one class, which is the players. But it doesn't know team A, it doesn't know team B, it doesn't know what they're wearing. And the goal is for the model to distinguish between team A and team B. And this is exactly what we're gonna do. So the model doesn't track individual or know which team they are on. It just labels all the players as a player. So how do we tell which team is which without manually tagging anyone? So first, you might think the best way is to grab a bonding box and average the colors inside. And that won't work. The reason is that because if you were to do so, then you average the shirt, the shorts, the socks, and even the tone of the grass. The result is going to be just muddy, useless blob. That's not a good solution. So the solution is simple. So we slice that bonding box right in half and just take the top half and throw the bottom. And the reason is that because the jersey in the top half. But we still have another problem. We still have a green grass leaking into the corners. So in step 2, we just get rid of that green grass. So in order to do it, we have to convert the image to HSV color space. So you might ask, why HSV? Well, there's a problem with the standard RGB color. So green is a messy dangle smear, but HSV, it's just a clean wedge on the color wheel. So what we need to do, we just filter out the green hue, sweep the image, and we left with the pure jersey pixels. Now we average those remaining pixels and we turn each player's jersey into a single pure color dot. And we do it for all the 20 players on the pitch, and we got 22 color dots. So if we plot these dots in a 3D space, something magical happens. So they naturally group into 2 distinct clusters, one for the blue team and one for the red team. Now to tell the computer where the teams are, we use k-means clustering. So basically we ask the computer to automatically split everyone into 2 groups. It finds the center of each group and separate them into teams. No manual labeling required at all. But we're not done yet, because there's another problem. If you run k-means afresh on every single frame, those center jitter, the dots shake, and the team colors on the player flicker like crazy. And it looks terrible on video. And that is an easy fix because we can use exponential moving average or EMA. So instead of jumping to a new center immediately every frame, we only nudge the center by 8%. So one bad frame of noise barely moves it, but real changes are still tracked very smoothly. And that's it, we have automatic team detection pipeline. Okay, let's get into coding. We'll add custom annotations and also prepare team assignments based on what we've described before. First, let's import both of libraries CV2 and NumPy, and then we can add constant, draw ref, and draw balls just to basically let you easily disable drawing markers for referee and ball if you don't want them in a video. Next, we have the draw annotation function. So this acts as your digital paintbrush, looping through every detected object in the frame and drawing the correct mark based on who or what it is. So for example, if the ball, it adds a yellow triangle point down and a small circle on it for visibility. For the referee, we draw 2 centric ellipses at their feet to set them apart from the players. And finally, players, we show team color with solid triangle above their head. And next we have the team tracker class. So basically this is the brain for figuring out which player belongs to which team. It ensures team color stays stable across the whole video, so rather than just a flickering frame by frame. So this class uses k-means clustering to split player colors into 2 teams. So it computes the average color for team A and team B, and then assigns each player to the closest matching team, and it gradually updates the color memory for the next frame. And finally, we have the jersey color function. So it determines a player's shirt color while ignoring the background. So it's based on 3 different steps. Crop, masking, and calculate. For crop, it crops the top half of the player's bonding box, and then the masking, it converts the HSV and removes the green pixels to avoid the grass interference. And finally, it averages the remaining pixels to get the dominant jersey color. And finally, we pass this component to the main file, index.py. And what we need to do, just 2 things. First, importing, so we can import the custom markers component that we just made, and then we can do the execution. So the execution, there are 2 parts. First, so we pass all the detected shirt colors into the tracker.assign function to get the team IDs and team colors. And secondly, it feeds those assignments right back into draw_annotations to actually stamp the graphic onto the video frame. And finally, we can run the model to check the results and see the new annotations that the model started drawing. Okay, now let's implement ball possession. I've seen many approaches where they try to measure the ball distance from the center of the box to the ball, and the problem with that, the center of the box is too far from the player's feet, and that would lead to misidentifications. So instead, we measure the distance to the box's nearest edge using just a quick mini max clamp. So if the ball is inside the box, the distance is 0. Obviously, if it's outside, we just calculate the distance to that edge. Now, how do we do the actual tracking? So the way we do it, we just drop an 80 pixel boundary ring around the players. The ball enters the ring, the team starts racking up frames, and once they lose the ball or the ball is nowhere, nobody gets any point. And to get to the final possession percentage is really simple. So we just divide each team's frames by the match total. Because it builds up over the whole game, the possession bar stays smooth, and one noisy frame or a quick pass won't make it swing widely. And that should be enough to give us very accurate possession bar. Okay, let's create a component called possession.py, and this is where we start off with. So first, to import, the only import that we need is going to be just math. So first, let's create the possession tracker class, and this class acts like a referee stopwatch. So you set proximity limit of 80 pixel, and it keeps simple counter for both teams. So each frame, it finds the ball center and measures the distance to the closest player. And if that player is within the limit, it adds one frame to their team's tally. Then it turns those raw counts into clean percentage, defaulting to 50-50 if no one has touched the ball yet. Now we need to render it. So we're going to add draw possession function to the custom markers component. And this is going to add the bottom screen bar that shows the percentage. It draws two rectangular side by side where teams A width changes based on their possession percentage, obviously, and teams B takes the rest. Then it slaps the percentage number right next to the bar so viewers can read the stats instantly. So finally, we can import the possession engine into our main file. So there are going to be 3 different steps to do so. So first, during our initial setup, we initialize the new possession tracker right alongside our existing team tracker. Secondly, inside the AI loop, we add a quick filter. After the AI scans the field, we isolate the exact coordinates of the ball and feed that alongside, obviously, the players directly into our new possession tracker. It instantly calculates who has control based on proximity. And finally, we need to render our results. So we simply call our new draw possession function. It takes those freshly calculated percentages and team colors and stamp a sleek possession bar onto the video frame right before it renders it out. Then we can run the script to check the results and see how it looks like. Okay, into the last part, which is tracking. So in this part, we're going to do advanced tracking. Specifically, we're going to do player speed. So we're running YOLO on a football match, and you want to measure a player's speed. Sounds easy, right? Distance over time, like you learned in school. Wrong. You have 2 massive problems. 1, YOLO has 0 memory, and 2, camera never stays still. First is the memory problem. YOLO sees each frame alone. It doesn't know that player in frame 2 is the same player in frame 1. So we need a cheap way to fix that. The way we do it, we see how much 2 boxes overlap. If there's a lot of overlap, basically it's the same player, and then we just give them an ID, a permanent ID to track them. So now this is sufficient enough, and now you know who's who, but you can't measure the speed yet. If camera pans left, a goalie standing perfectly still looks like he's sprinting right, and we need a virtual tripod. So our goal is to lock the camera. We take our YOLO boxes and use them to block out all the players, and we only want to look at the background. And by tracking how the grass and lines move from frame to frame, we can mathematically cancel out the camera pan, and boom, we have a locked camera. Next problem, a player far away looks tiny. So pixels don't equal meters the same way for everyone. So to solve this problem, we convert pixels to real world meters. We assume an average player is 1.8 meters tall and divide that by their box height in pixels. And this is the cheat code for depth. Because a player farther away has a smaller box, the scale adjusts automatically. Finally, we put everything together, so we track the bottom center of the box. Well, actually especially their feet, over 8-frame rolling window. But the issue, bounding boxes naturally wobble, making standing players look like they're crawling. So to fix this, we add deadband filter to force slow speed to 0, and also at the same time capping the max speed to 40 kilometers per hour, and try to smooth the rest of it. And the results are amazing because you get persistent IDs and highly accurate real-world speed tracking, all from a moving camera. Okay, let's move into coding. So the first thing is I'm going to create a component ID tracker, which is the memory we just talked about. It takes YOLO amnesiac frames and stitches them into a timeline. It's broken into 3 different steps. First, we set the ground rules. So we have the IOU thresh, the max age, and TR. So TR basically the trackers. So the IOU thresh is basically how much the boxes need to overlap to be considered the same player. As for the max age, it's basically how many frames do we remember a player who disappeared behind someone else before we delete them. Finally, for the tracker, this is the actual memory bank where we store everyone's ID and current box. Next, overlap checker function, the IOU. So it looks at 2 boxes, one from the last frame and one from the current frame. It calculates the intersection over union, the IOU. In plain English, how much do these 2 rectangles overlap? Spits out percentage. 0 means completely separate, 1 means a perfect match. Next, we have the engine function. This runs every frame and it does 3 things. So first, we ignore stuff that we don't want, like the ball, the referee, so they don't get IDs. Secondly, we match each player to their old ID by finding the box with the most overlap. It's the same what we've talked about in the animation. And third is birth. If a player doesn't match an existing ID, then we give them a new one. And finally, if an old ID does not match any player for too many frames, then we just delete it. Next, let's build the speed tracker component, which is the speedometer we just talked about. The camera is always pinning, so this component's job is to figure out how much the camera moved and calculate the player's actual physical speed. And so it's broken into 4 simple parts. First, let's import the libraries, which includes CV2. Then we need to set the stage. So the first important one is the FPS, frame per second. We need this to know how much real time has passed. Next, H_M. So the magic number here is 1.8. So we assume the average player's height is 1.8 meter. You could change it to whatever you want. We use this to figure out how many pixels equal to 1 real world meter. And then we have the filters that we talked about before, the window, the alpha, and deadband. Next, the stabilizer_cam. It draws a block box over every player so we can completely ignore them, then finds highly textured point on the grass or stadium. In plain English, how much did the background move between the last frame and this one? It saves the camera movement into mathematical matrix so we can subtract the camera's pan from the players later. Next, we have the math engine, the update function. The main goal of this function here is to turn pixel movement into real kilometer per hour. And it does that by looping through every player with an ID. And it does 3 different things. First, it looks at their height of their bounding box to figure out exactly how big a meter is in that specific part of the screen. Secondly, it calculates the real speed. So it looks at where the feet were a few frames ago, calculates the raw distance, divides by time, and multiplies by 3.6. And it outputs their speed in kilometer per hour. If they were barely moving, it just forces the speed to 0, so stationary players don't show speed. And finally, the UI draw under speed. It loops it through the speeds we just calculated. If a player has a valid speed above our minimum threshold that we set before, it renders it and it drops a clean dark rectangle directly below the player's feet and prints the text like 10 kilometers an hour in white. Now let's add the speed tracking to our main component. First, to import both ID tracker and speed tracker. Then we can import the NumPy library for speed trackers matrix math. Next, we can set the boolean for ball and referee, whereby you can disable or enable the speed tracking for them. Then secondly, we can initiate tracking. So we fire up the trackers right before the video loop begins. Then we replace the old filter. It checks the YOLO label. If it's a ball, use a speed_ball. If it's a ref, use speed_ref. Right before we draw everything at the end of the loop, we wire the new trackers. It's a clean 1, 2, 3 kind of step. So the first one, we just assign the ID to the masked box. Then we compute speed for anything with an ID. And finally, we render the labels on the screen. And finally, we can run the script to check the results. And as you can see, it tracks the players, the ball, the referee, and it shows possession and it shows the player speed. Okay, that's the build. Hopefully you enjoyed it, and that's the end of the tutorial. The repo's linked in the description. Clone it, run it, break it, do whatever you want with it, and I'll see you in the next one.
Frame rate locked, 0 delay. Calculating vectors, watch the play. Tracking every pixel in the grass. Anticipating lanes, I see the pass. Binary vision.